All right, let's get started. The first things we're going to talk about are points, lines, and planes. And we're going to start out just talking about a point. A point is just, a single individual location in space. There's a point. And then the question here is, how many different lines could go through this one point? Anybody have a thought on that? How many different lines could we draw through this one individual point? And it's okay if you don't. Many. I like that answer. That's very good. That's a great answer. Infinite. That's a perfect answer. Yes, because I could draw this line going through there, or this line going through there, or this line going through there, or this line going through there. There's an infinite number of lines that I could draw through any one point. So that one point out there in space doesn't really cement a whole lot of things for us because we could draw an infinite number of lines through it. When we move on to 2 points now, things change a little bit. When I have 2 points, and they don't necessarily have to be that way, they could be this way. Now I have 2 points. How many lines can I draw that go through those 2 points? How many lines are there that will go through both of those points? Perfect, Lorraine. There's just one. There's just one line I could draw. Hopefully it's a little straighter than that. Let me try again. There we go. That's a little better. There's just one line I could draw that goes through 2 points. There's only one line that can go through those 2 points. So if I have 2 points, they sort of define a line for me. You may remember that when you were graphing lines in an algebra class. Once you have 2 points, you can draw the line. You might have found a third one just to sort of make sure, but once you have 2, that's enough to draw the line. Then we get to a question that's a little interesting. How many lines can go through 3 points? And for this one, I'm going to let you off the hook. And I'm going to say this depends. It depends on how those points are arranged. If those points are arranged like this, then there's no way I can have one line that goes through all 3 points. Because if I try to do something like that, that's not a line anymore, that's a curve. So I could draw a line this way that goes through 2. I could draw a line this way that goes through 2. I could draw a line that way that goes through 2. But there is no individual line that will go through all 3 of those points. However, it could happen that those 3 points are drawn in such a way that, sure enough, there is one line that could go through those 3 points. When this happens, we would call those points collinear. Points that are on the same line are called collinear. So what we could say here to answer this question of how many lines can go through 3 points, well, one line if those points happen to be collinear. And so that's a new definition for us there. Collinear are points that lie on the same line. Since we have collinear, then as you would probably guess, we would say that these points over here are non-collinear. Those 3 points are not on the same line, and so we can't draw a single line through those. Up next, we're going to talk about planes. And probably an easy way to think about a plane, it's really just 2 dimensions. But if you sort of think of a piece of paper, it has a length, it has a width. And yes, technically a piece of paper does have a tiny little bit of height, but just imagine that it's only 2 dimensions, a length and a width, and that's all there is to it. That's an easy way to think of a plane, is sort of as a piece of paper. And if we have 2 points, we can draw an infinite number of planes through those. And you can imagine taking your piece of paper and sort of holding it on either side and then rotating it forward and backward. And you've got an infinite number of planes that can go through that one individual line. Visual things like this can be something of a struggle for folks who aren't necessarily that visual. I can tell you that I have to work pretty hard to imagine things when we start getting into planes. But that's okay. We are just going to sort of touch on planes very briefly. It's not going to be something that we spend a ton of time on. So I don't want you to become anxious or overwhelmed with the idea of what we're going to do with planes. It's going to be pretty basic and straightforward. And this idea here that if we have this line, there are an infinite number of planes that could go through that one line. Then when we get into points, and if we have, excuse me, three non-collinear points, so they're not on the same line, they're like this, those three non-collinear points define a plane. We saw earlier there's not one line that could go through those 3 points, but we could have a plane that goes through those 3 points, and there's only one of them. There wouldn't be a way to rotate this so that it went through all 3 points. So these 3 points, or any 3 points for that matter, would define a plane. And a really good way to remember this, and a good way to illustrate it for kids if you're talking about planes, is if you think about a stool that has 3 legs. If you take a 3-legged stool, and you don't see those very often, it's kind of unfortunate. If you take a 3-legged stool and you set it on the ground, it won't wobble because the plane that it's defining is the floor. That 3-legged stool won't wobble because it's defining the plane that is the floor. If instead you have a 4-legged stool, it can wobble because now you've got 2 different planes you're defining depending on how those legs might wobble back and forth. But a 3-legged stool won't wobble. 3 non-collinear points define a plane. Now we'll get into stuff that's probably more familiar, probably more comfortable: lines, segments, and rays. So the first thing we're going to talk about is a line. And a line is something that goes forever in both directions. It never ends. It goes on forever in both directions. And if we have points that are on that line, say A and B, then we could name this line. And the notation we would use to name that line, we would call it line AB and use that symbol over the top. Because lines don't really have a direction, they could go either direction. It goes forever in both directions. You could also call this line BA. That would be perfectly fine. It's common for us to name them in alphabetical order. If we have a choice, we'll go alphabetical order. But there's nothing wrong with calling this line BA. It's the same line. What we're saying there is we're talking about the line that goes through the points B and A. And that's this line right here. Please let me know if you have any questions or if there's anything that comes up that you want to ask about. Like I said, a lot of definitions and information today. So there's not a lot of chances for me to ask you questions. I'll try to do my best when the opportunity arises, but don't hesitate to ask questions if you have them. Then a line segment. A line segment is just a piece of a line that goes between 2 points. It doesn't go on forever in each direction. Instead, it has a place where it starts and stops. And it could go between points A and B. And the way we would indicate that it's a line segment is we would use AB as our points, and we just put a bar across the top. Without the arrows, we're indicating that it doesn't go on forever in each direction. Just like the line, this line segment could also be called line segment BA. That would be just fine because it's a line segment that goes between those 2 points. Finally, we have a ray. Now, what's different about a ray is while we need 2 points to define that ray, a ray definitely has a direction. So a ray goes on forever in one direction, and if it's from A towards B, now there's only one way we can name this, and that's ray AB. And that's because this ray happens to start at A and go through B. And so it's ray AB. We're keeping the direction in mind when we name that ray. It doesn't have to be in alphabetical order, though. I mean, a ray could certainly go start at B and go through A. And if it starts at B and goes through A, then this one down here would be ray BA. And yes, the ray points to the left, but we're always going to, with our notation, just have the arrow pointing to the right, even if the ray goes the other direction. And we would know which direction it goes because these points tell us. It starts at B and goes through A. And I'll kind of pause when we get to the end of each of these to give you a chance to ask questions you might have. And please don't hesitate to tell me, can you go back? I didn't get all that, or there's something I wanted to ask about the page that we just finished. If I go too fast through them, you just let me know. Different types of lines. We have lines that can be parallel to each other. Parallel lines never intersect. And I'm also going to throw in this caveat that they are in the same plane. That'll make more sense in a few minutes, but parallel lines never intersect. They're in the same plane, like those two lines right there. They go on forever in both directions, but they never intersect. They're in the same plane. That's what makes those parallel lines. Perpendicular lines do intersect, but they intersect in a special way. How do perpendicular lines intersect? There's a chance for me to ask a question. I'll throw it out there. And if you don't know, it's okay. But if you do, you can help push us along a little bit. What is special about perpendicular lines? Yes, they intersect. How do they intersect? What happens when they intersect with each other? Perpendicular lines. And it might not be that easy to phrase, but that's okay. We're not scoring anything. Perfect, Lorraine. That's what we were after. They intersect in a way that makes a 90-degree angle. Perfect, Nicole. That's excellent. So they intersect to make a 90-degree angle. So for example, perpendicular lines could be like that. So we have two lines that intersect. And to identify that 90-degree angle, it's typical for us to put a little square in there to show that they've intersected at a 90-degree angle. The last one, and this is a word you may not be familiar with, concurrent lines, is when three or more lines. Yes, exactly, Lorraine. You're exactly right. It doesn't have to be vertical and horizontal like I drew it here. It could be rotated a different way. We could have perpendicular lines that are at an angle instead of one of them being vertical and one of them being horizontal. But if they intersect and make a 90-degree angle, we're going to call them perpendicular. The last one we'll look at here is concurrent, and that's when three or more lines intersect at a single point. So, and that's something that we kind of looked at our very first example of how many different lines could go through one point. We can have more than one line intersecting at a single point, or three or more lines intersecting at a single point are called concurrent lines. That's not a word we use that often, but I do want you to be aware of it. One other type of line that we're going to look at may be new for you. It's the reason that we mention that parallel lines have to be in the same plane, and they're called skew lines. Skew lines do not intersect. That's an important part of skew lines, but it's not because they're parallel. Parallel lines are in the same plane, and they just happen to never intersect with each other. Skew lines, we wouldn't call them parallel because they're in different planes. And as we look at this, sort of imagine a box or a cube here. On the front side of the cube, here we have line AD, and then sort of going from front to back on the bottom corner, we have line EF. And they never intersect. There's no point where they come together, but it's not because they run along the same line. BC, for example, would be parallel to AD because they're both in this plane right here at the top of our cube. Those would be parallel lines. But AD and EF, they're not parallel because they're not in the same plane. These are skew lines. And the reason they don't intersect is because they're not even in the same plane. They don't have a chance to intersect. And that's skew lines. They don't intersect because they're in different planes. All right, let's talk about some angles. Angles are a union of two rays and have a common endpoint. That common endpoint is called the vertex. That's a very formal way to define an angle. My guess is most of you are pretty familiar with the idea of an angle. But using the terminology that we've talked about today, we can see here that this is the union that's joining together of two rays. So I have this ray and I have that ray. And when I join them together, I've created an angle. And it has a common endpoint right here. Those two rays have a common endpoint. They start at the same place. If we were to label this A, B, and C, then up here we have ray AB, and down here we have ray AC. So it's the union of two rays that have a common endpoint. That common endpoint we're going to call the vertex. And so this angle has a vertex that is point A. If we want to name the angle, and it's important to know how to name an angle. If we want to name this angle, what we're going to do is we're going to start at one of the points, then mention the vertex, and then mention the other point. So we could call this angle BAC, because if we were to start at B, go to A, and then go to C, we have described that angle that we've created there. This is angle BAC. If you wanted to, you could also call this angle CAB, because you're starting at C, you're going through A over to B, CAB. When there's only one angle involved, you can name it with the vertex. If you wanted to just call this angle A, you could, as long as there's no chance for misinterpretation. What I mean by that is if we also had, say, point D over here, now we wouldn't want to call this one or this one angle A, because A is the vertex of more than one angle. So this is no good now. That could be confusing. We don't know which one we're talking about. If we wanted to talk about this angle, we could call it angle BAC. And then if we wanted to talk about this angle over here, we would call it angle BAD to describe that one. Let's look at some different types of angles. 4 different types of angles that we're going to talk about. A right angle is something we've already sort of alluded to a little bit. A right angle is a 90-degree angle. And so if we have a right angle, it's going to be 90 degrees. Doesn't have to be vertical and horizontal. It's just a really nice, easy way to draw it. A straight angle is one we don't talk about that often. A straight angle has a measure of 180 degrees. A straight angle would just be part of a line like this where, let's say we have point A, point B, and point C. And if we're looking at the angle that starts at A, goes to B, goes to C, this angle right there is 180 degrees. That's a straight angle. We could call it angle ABC because it goes from A, then to B, then to C. B is the vertex here. They're the union of two rays. It just happens to be along a straight line. And that's why we call it a straight angle. Measures 180 degrees. An acute angle is any angle that's less than 90 degrees. So any angle less than 90 degrees, like that one right there, would be an acute angle. Angle BAC here would be an acute angle. And then an obtuse angle is any angle that is larger than 90 degrees. So this angle here would be bigger than 90 degrees. That would be an obtuse angle. And we saw one of those back here. Angle BAD would be an obtuse angle. Again, feels like we're kind of going through a whole bunch of terminology pretty quickly. If there's anything where I've gone too fast, you need me to go back, or you have any questions, let me know. Mostly just definitions today. That's just setting us up for our geometry study. Okay, terrific. Adjacent angles. Formally, adjacent angles have the same vertex, they share a common side, and the interiors are disjoint. Informally, there are two angles that are next to each other. So let's look at that formal definition just for a second. They have the same vertex, they share a common side, and the interiors are disjoint. So there are a couple different examples of adjacent angles on here, but probably the easiest to see are angle DBE, which would be this angle right here. That's angle DBE. If you're not sure how I named that, please don't hesitate to ask. And then angle CBD, which is this one. Those two angles are adjacent. Formally, they have the same vertex. Yes, they sure do, because as I look at how I've named it, I've got B as the vertex and B as the vertex. If I look at the picture, I can see that B is the vertex of each of those angles. They share a common side. Well, this side right here, DB, it's a part of angle CBD. It's also a part of angle DBE. So they do share a common side. And then the interiors are disjoint. That's very formal language to say, if we look at the inside of CBD and we look at the inside of DBE, they have no overlap. They are distinct from each other. They don't overlap each other at all. That's what disjoint would mean to us. And so that makes those two angles adjacent. Informally, which I think is great. This is kind of how we'll talk about adjacent angles just in normal conversational language. They're next to each other. When I look at CBD right here, it's right next to DBE. The fact that they share a side is an important part of that being next to each other, but that's what adjacent angles are. If we talk about adjacent angles, we're talking about two angles that are next to each other. There's some other terminology. I want to take advantage of this picture to discuss. If we look at this picture, and I'm going to get rid of all my scribbles here real quick. If we look at this picture and we kind of see that one of those lines, well, line segment AE, is horizontal and line segment BC is vertical. So together, those two angles would make a right angle. So I've got a right angle right there. I could say that line segment AE and line segment BC are perpendicular because they make a 90-degree angle when they intersect. What this means for us, because there's a right angle right here that adds up to 90 degrees, what that means is that this angle, when added to this angle, make a 90-degree angle. So angle DBE, angle DBE, when added to angle CBD, those two added together add up to 90 degrees. I don't know what the measure of DBE is. I don't know what the measure of CBD is, but I know when I add them together, it makes a 90-degree angle. When this happens, when two angles added together make a 90-degree angle, we call those angles complementary. Those would be called complementary angles because they add to make a 90-degree angle. It's another word that kind of goes right along with this one. If we look all the way here, we have a straight angle. So there's a couple different ways that I could combine angles here to get to a straight angle. If I use angle ABD and I add that to angle DBE, oops, if I add those two together, it makes 180 degrees. And if I have two angles that I add together to make 180 degrees, we have a name for that. Those are called supplementary. Two angles are supplementary if they add to 180 degrees. There's other ways I could do supplementary here. As I look at this picture, let's see. I could do ABC added to CBE. So let's see, ABC added to CBE. Those would also be supplementary because they add to make 180 degrees. Any questions about anything there with adjacent angles, complementary angles, and supplementary angles? All right, fantastic. Vertical angles. Vertical angles are back to back. What I mean by that is this. Let's say we had this picture right here. I want that to be less perpendicular. Yeah, that's better. And you know what? I'm not going to name these with letters. Instead, I'm going to use numbers to name them. That's something that we do occasionally. And to use numbers to name these, we just kind of put the number right in there. And that means that this angle right here, we're going to call that angle 1. So we can use letters to name angles. That's probably the most common way we'll do it. But there are times when we'll just kind of stick a number right in there close to the vertex. And then we're going to call this angle 1. And we'll do angle 2, angle 3, angle 4. So we have 4 angles in this picture, angle 1, 2, 3, and 4. And when I say vertical angles are back to back, the more formal definition would be that they share a vertex and they don't share any sides. So let's take a look. If they share a vertex, but they don't share any sides, that could be, in this particular picture, that could be share a vertex, but don't share any sides. That would be angle 1 over here on the left would be a vertical angle with angle 3 over here on the right. They share a vertex, but they don't share any sides. I tend to just say they're back to back, but probably a more formal definition is they share a vertex and they don't share any sides. Let me jot that down real quick. One thing that's really useful and valuable about vertical angles is that they are equal to each other. This will be important for us later on when we start trying to find angle measures in a picture that has a bunch of different angles in it. But what that means is whatever the measure of angle 1 is here, angle 3 has the same measure. And then also, because in this particular picture, angle 2 here and angle 4, those are also vertical angles. So whatever the measure of angle 2 is, angle 4 has the same measure because they're vertical angles. All right, we do have that. That's sort of our definition part of today, and honestly, that's the vast majority of what we're talking about today. We do have a couple of finding angle measure problems to look at. I think they're kind of fun. Let's take a look at those. What angle is made when it's 9 o'clock? So first of all, we have to realize we're talking about an analog clock. So we've got our clock here with 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so there's our clock, and we're saying it's 9 o'clock. And so I've got an hour hand pointing at the 9 and a minute hand pointing at the 12. What time is it when it's 9 o'clock? Or excuse me, what time is it? What angle is made when it's 9 o'clock? And what we're talking about is this angle right here. Very good, Escadar. Lorraine, it's a right angle, which means it's how many degrees? Excellent, Escadar. Perfect. That's a right angle. That is a 90-degree angle. Now, that one we could kind of do visually and inspect it. What I want you to imagine, though, just for a second is, what if we couldn't do it visually? How would we figure out the degree measures? And I'm going to give you a chance to try it. It's okay if you don't get this right. We're just sort of exploring right now. I want you to try this one, and I'll set up a poll for it. What angle is made when it's 10 o'clock? Like I said, I'll set up a poll for this one and give you a chance. One thing I will tell you is I don't expect you to get out a clock and a protractor to do this. You could, but you don't need to. What angle is made when it's 10 o'clock? And what we're talking about is the angle between the hands, between the hour hand and the minute hand. We'll go another 30 seconds on this and then talk about it together. And I'm pretty sure that a question like this is in the homework, and then you can kind of expect to see it on the quiz or an exam. Take a look and see where we are on this. Okay, not unanimous, but strong agreement. That's a good place for us to be. That's typically where we come in, and that's a good place. That means that we're probably doing pretty well, and it also gives us something to talk about. So it's 10 o'clock, so we'll have our clock here with 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Doesn't have to be perfect. We're just after a sketch here to give us an idea of what our clock looks like. And when it's 10 o'clock, our hour hand's pointing at the 10, our minute hand's pointing at the 12. And what we're interested in then is how big is this angle right here? Well, what we knew was that it was 90 degrees when it pointed at the 9. So we might go from there and say, okay, well, since it was 90 degrees when it pointed at the 9, then this must be 30 degrees, and this must be another 30 degrees, and this must be another 30 degrees. And that's a perfectly reasonable way to think about this. Another way to think of it is when we talk about a circle and going all the way around a circle, that's 360 degrees. We have 12 hours on our clock. So if we take those 360 degrees and divide by 12, we find out that there are 30 degrees between each number. So you could have gone from what we worked on in the last one being 90 to say, well, then these must be 30 each. And that's exactly right. Or something like this, where if it's 360 degrees all the way around the circle and there's 12 hours in the circle, we'll divide and find out that, you know what? Every time I go from one number to the next, that's 30 degrees. And if that's true, then I've got 30 degrees here and 30 degrees here. And so together, the angle that's made when it's 10 o'clock must be 60 degrees. Let me know if you have any questions on that before I have you try another one. Okay, this one's tougher. You might get mad at me and say it's a trick question, but after we talk about it, you're not allowed to say that anymore. What angle is made when it's 6:30? I'm going to set up a poll for this one and give you a chance to try it. So be careful with this one. That's my advice. We'll go another 30 seconds on this and then talk through it. All right, let's see how we did on this one. Okay, very similar. Strong agreement, but not unanimous. All right, very good. Okay, so let's take a look at this one. So I'm going to start by drawing my clock again. Um, and let's see, we'll have our big circle and we'll have 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. A really key part of this one is where do those hands go when it's 6:30? Because while your first instinct might be, well, the minute hand points at the 6, and the hour hand also points at the 6. But that's not how a clock works. And this is where the, hey, that's a trick question might come into play. When it's 6:30, this hour hand is halfway between the 6 and the 7. And that's how we wind up with an angle in here that's not 0 degrees, because when it's 6:30, the hour hand is halfway between the 6 and the 7. And so we do have an angle in here that's not 0. And well, halfway between, what the heck is that going to be? Well, I don't know. We kind of figured out that if it's 30 degrees from one number over to the next, if it's halfway over, then the angle that's made here when it's 6:30 must be half of that 30 degrees and be 15 degrees. That was the most common answer. You did great with that one, because I think it's a pretty hard question to answer. And once the quote unquote trick part gets removed, then it's like, oh, okay, now I get it. But at first glance, that might seem a lot harder than it really is.